everybody. So we will start the 15th Meetup, Deep Learning Meetup. My name is Ollion and I'm glad to be here tonight with all of you here. We organized this meetup with Heuritech and Microsoft. We are a startup incubated at the Microsoft AI Factory. So before I start and let Andrew do the first talk, I just wanted to take 3 minutes to talk a bit about Heuritech. So Heuritech, we are machine learning experts on NLP at first, but nowadays rather on computer vision. And we are focused on vertical applications, especially fashion, on which we have several customers today. And I will be telling you just a few things about what we do and how we do them. We are a big team of now almost 30 people and still a very technical team. A lot of people working on computer vision models, very close to academia, but also a lot of engineering to put that into production. So feel free to check out the papers. One was recently accepted at Denoising by Eddie, who is here. And so what we do is we take images and videos from social media, and we are able to analyze them and detect all the characteristics of fashion. From the general aspects of the clothing, the shoes, the bags, the different textures, patterns, colors, etc., up to very precise products, such as the exact model of the handbag, of the shoe, when they are recognizable. So this is a quite difficult problem because we are in open set domain. So images that can come from anywhere that are not all related to fashion, and we are trying to detect objects of fashion within them. So there's a lot of difficulties in that, and we have a lot of research and engineering to do that efficiently. And in addition to a lot of computer vision, we use all this data to help brands predict trends. And we developed a whole application and data science expertise to predict the trends, to anticipate what's going on, to anticipate the sales and the stocks from this social media information. And nowadays we have both the people working to computer vision, processing all the pictures and videos every day, and the people building the tools to anticipate the trends and make this data actionable for brands and retailers. So without further ado, I will now introduce the speakers. I don't want to talk too much about Heuritech, but we are several here in the room, so if you are interested, you can come and discuss afterwards. So we will start with Andrew Fitzgibbon, senior researcher at Microsoft, working on a lot of projects in computer vision, who will be talking as a first speaker. So please welcome Andrew. Looks good, so Andrew.
Merci bien, je suis ravi d'être ici. Comme aujourd'hui, that's about the extent of my French, so we'll proceed in English. I'm really pleased to be here, a little bit intimidated because, computer vision person in deep learning space, but I'm just going to talk about optimization, which is a problem we all face, so we should be able to speak the same language. I'm also going to talk a little bit about I've been sort of lucky enough to be involved in a few examples of computer vision systems that became real world products. And sometimes I was kind of involved like the pig in the ham and egg sandwich, and sometimes I was involved like the chicken, and sometimes I was involved like the person who was behind the person in the queue getting the sandwich. But nevertheless, the things that I've been associated with, or I'll show you one which is building software for the movie industry, which we did a long time ago as a startup before I joined Microsoft. And I was involved in the Connect for Xbox 360 project, which was maybe one of the first projects, I was thinking about this recently, where we went out and commissioned huge amounts of label training data. We used synthetic training data for Connect, and I was just thinking back that Before that, Occams and other people had used masses of training data for postcode reading, but then for Connect we had this sort of synthetic training data thing. And then recently I've moved to work on this device here. Who knows what this device is? Okay, not loads. It's a HoloLens. I'll show you more about it. It's a very exciting thing to work on, which I hope I'll convey. I have another message that I want to convey to the world, which is I like the way at Microsoft with Kinect and HoloLens that we've managed to blur as much as we can the distinction between research and engineering. And once when I was young, I don't know, 25 or something, I was working in Edinburgh, and an Italian postdoc introduced me as, here's our engineer. I was never more insulted in all my life. I couldn't believe that somebody would say that. Number one, when Italians say you're an engineer, it's actually a good thing. And number two, it's actually a good thing, right? So, whether you're doing research or engineering, the thing I think that makes a difference is if you can change the lives of people. And I don't mean every person has to use it. I mean, if you write a software library that 20 people use and are happy with, you've done a good thing for the world. Is that research or engineering? It depends, it depends on a bunch of stuff. The other thing is, we think of doing stuff that was never possible before, and I'll show you this HoloLens device, and it's amazing, and it really is a huge advance. And yet, it's all stuff that we knew we ought to be able to do, but just the final twist, making it 100 times better or 10 times better, is sometimes, for me, as exciting as proving any theorem. So what is the HoloLens? It's a device that you wear on your head. It has transparent screens. So it's like a VR headset. It's an augmented reality device or a mixed reality device. It's where transparent screens show you overlaid computer graphics on the real world. So this person is in a featureless kitchen, a sort of model kitchen in some putative showroom. And overlaid on the center of her field of view is a 3D rendering of exactly the same scene, but now with different textures, maybe different models of oven and some informational panels. And we can overlay the 3D geometry onto the real world. And the crucial component of this is that as you move your head, the image is continuously re-rendered so that you always get a perfect 3D perception of what's happening in the world. So the device has to, in the space of about -6 milliseconds, which isn't a lot of time, figure out where it is in 3D, and I'll talk a little about that. You can probably imagine various uses for the device, but anything where you're conveying information from one human to another. So you're teaching anatomy, or you're talking to industrial clients about a new architectural installation that you're creating. It's clearly going to be helpful to transmit three-dimensional information to other people. It's also surprising, actually, it's useful in any situation where somebody has to work hands-free. So when we first conceived of Connect, we kind of showed examples of Minecraft, and we showed examples of people having fun with Connect. With the HoloLens. We didn't realize that it would be immediately useful in lots of business scenarios. I'll only show you a short video of this one, but I really like it. It's a very important use case. So this is the scenario where you need to create a new hipster shoe store, and you found yourself your hipster location, and now you need to visualize what's going on. So the HoloLens is locating itself just using the features in the environment, just using onboard cameras, so everything's self-contained in the device. And now you can place 3D models into the environment, move them around, see how it's going to look. Sometimes you decide it's not going to look very well, so you're going to throw it all away, and you're not annoying at all, I assure you. Virtual Assistant is going to help you to, find another hipster, and then you can work on it together, and it's all going to be great. So it's an amazing device. I'm sure you can imagine lots of things you could do with it. Let me break it down a little bit, because I really like it. What's in it? So we have a collection of cameras, 4 cameras looking out at the world, which will tell the device its position in the world, its position and its orientation. A camera at the top, a depth sensor, which is derived from the technology used in Kinect for Xbox 360 for video games, and then sort of cameras that you can just use to do Skype, or you can use to interact with people on the world. The head tracking cameras are interesting, and this is not work I did, but my colleagues did, which I just think it's amazing. We released it 2 years ago when it was industry leading in accuracy, and in a sense, people haven't caught up yet. So sometimes if you do your engineering incredibly well, you know, it takes a long time for people to catch up. Is that research or engineering? I don't know. The technologies before HoloLens was released for virtual reality displays, typically, and AR displays, involved, as shown on the left, installing some infrastructure into the environment. So something like the HTC Vive has very neat, straightforward infrastructure, but nevertheless you need to plug stuff into the environment to give a point of reference for the device. Instead, the HoloLens just uses its cameras. When it switches itself on, it records a snapshot of what's happening in the room, and then updates that snapshot as it goes through the environment to continually hold its position relative to when it started. So what that means is, although the coordinate system was arbitrary when you started, whenever you place a hologram in the room, then it will always remain in the same place. So this is just giving you a view of the environment. Because of the processing requirements, we need to reduce the data stream to a very small amount. So you see these different colored dots, which represent the information we extract from the environment. So that produces incredibly accurate head tracking. There's another camera on the device, the depth sensor, and the depth sensor is used to measure other things about the environment and the environment near to the user. So, for example, something that I've been looking at, the depth camera is looking at your hands in front of the device and then detects whether you've made certain gestures or the position of your hands. The technology in the version 1 HoloLens is based on work we did for Kinect, where a random forest, who's heard of random forests? Okay, you know your history, that's good. A random forest is used to segment it, segment every pixel, or to annotate every pixel as one of a few classes, fingertips. You can probably guess the classes here. That's in V1. As you might imagine, in V2 we've replaced it with a deep learning engine, a low power, a very efficient deep learning engine, which gives us much nicer data. And the deep learning engine allows us to initialize a sort of traditional computer vision model fitter, which I'll tell you more about, which we would then be able to interact with stuff in the device as if we were just using the physics rules of the real world. So this is not footage from the device, this is footage from a paper we did at Microsoft a few years ago, where we're using a tabletop mounted camera. But the idea is that I can accurately measure the surface of your hand and then learn to do physics with the real world. Actually, there's something interesting in here which I think you might naturally think of. You might wonder, does it matter that there's no haptic feedback? Right, I'm just going to mess with my fingers. And I thought so. So I insisted that we made this very narrow user interface element, because I thought what would happen is your fingers would touch each other and that would kind of give you the haptic feedback and that would be okay. Actually, this motion, when you touch it with one finger and it moves away, it's amazing the strength of feeling you get, the haptic feel you get. In fact, the first time I did it, it wasn't on that, it was on a floppy bunny, but I actually thought that they had put some audio trick into the stream because it felt so real, but it wasn't. It's just your brain tells you. And my idea about the wafer thin control was irrelevant, but that happens. Okay, let me tell you about my other favorite bits of the HoloLens. Well, the screens are very good, and if you're into optical physics, they're a marvel. But I don't understand optical physics, so I treat them as something that I can just use. There's an inertial measurement unit, which is, of course, important to contribute to the head tracking. And then there's this very exciting thing, which is, in some sense, a rather unremarkable Windows PC, a sort of a mid-range Windows PC with a decent-ish GPU and a decent-ish system-on-chip CPU, which you use, which is what all the programming model on the HoloLens is. So you just write Unity apps, upload them to the device, it's really easy. And then there's this fabulous object, This fabulous object is a 24-core DSP with 24 500 megahertz processors on it. What's amazing when you're programming on this machine, so you just program it in C++, sometimes you use some sort of SIMD, vector instructions, but it's basically C++. What's amazing on this machine is every piece of slowness is the programmer's fault, right? If nobody else took my Dcache, I didn't miss the Dcache because somebody else was sitting there, right? I'm the only person running on the machine, so all the Dcache misses are my fault. When we brought our research code to this machine for the first time, we were already 10x better than the state of the art in terms of efficiency. We were running on a tablet CPU rather than on a massive GPU. We moved it to HoloLens, hit compile, hit run, figuring we'd be okay. My guess would be we would be 15x over budget. We were more like 100x or 500x over budget. So it's been really interesting to see how much time we waste in our computers. And we thought we were decent C++ programmers. So, but we all know this, right? The memory hierarchy is really, really important. It's really important to keep the machine busy. And I'm also going to claim that this is a super energy conscious, heat conscious, low power device, right? It lives on your head. It has to do all this computer vision stuff. But I think as we move on with our deep learning workloads, both training and test time and inference time, I think we are going to want to save 100x of energy use. We're going to start paying more for our energy use. And I don't have answers for how we're going to get there for classic deep learning workloads, but I hope that some of what I talk about might be helpful in getting there. All right, I want to tell you about optimization, just a little brief section on optimization. First of all, I thought it's really important that you hear my life story, right? Because otherwise, how will you understand the optimization? So my life story is I grew up in Cork in Ireland, where I did mathematics at school like lots of you. I had a job as a water taxi driver. That's not me. It wasn't that long ago, but that's the idea. Which was a great job because I was busy from sort of 8 a.m. till 10 a.m. and busy again from 4 p.m. to 7 p.m. So I had lots of time in the middle of the day to write programs and read books on mathematics. I went to Scotland to study, I thought I was going to study shape, the general concept, and I ended up completely obsessing on the ellipse. And I'm going to force you to live through my obsession with the ellipse, say in a few minutes. I went to Oxford, where I worked on building 3D models of rigid objects. And then I went to Microsoft, where essentially I'm interested in, can I build 3D models of something that won't stay still? So something like a dolphin which is leaping through the environment. Can I figure out what 3D stuff is happening from very limited data? But let me talk to you a little bit about shape. Okay, so what do you do when you have a problem involving data? Well, the first thing you do is you have a look at the data in some way, right? You find some way to plot it or scan through it. And over the last 2,000, 3,000 years, we've devised various ways that you might describe some data that you look at. So here are 3 data sets that I found. And if I asked you to describe those data sets, you might say, I would choose a linear model for the left. The second one might look like a quadratic model. And if you were living maybe 400 years ago, you might have said, or maybe 100 years ago, you might have said, I can see where you're going here. You want me to have a cubic model on the right. You may have more domain knowledge. You may think, I know that looks like a cubic model on the right, but I know this actually comes from some underlying periodic process. So I think what I've actually seen is a bit of a sine wave, maybe with a linear correction. This is all goodness, right? This is all perfectly reasonable, looking at the world and deciding what knowledge I have, what mathematical knowledge I have that I can put in there. But this is all so 19th century, right? What's this function, right? This isn't a special function. This is just something that happens in the very specific case of geometry of a circle. If you look at the code for sine in the computer, it's just some funny polynomial expansion. In the 21st century, obviously, what this curve is one quadratic pasted onto another quadratic. Right? We have a piecewise definition of the functions. We would never have done this a century ago because it would have been such a pain to analyze composition of functions like these, or to analyze interactions between these functions. But of course, once the computer comes and we have the concept of splines and piecewise functions, this is actually a very natural, stable way to describe data. And then, of course, you can take that to extreme. You can say, well, why are you chaining quadratic forms together? Why don't you just chain, something which is linear on one side and flat on the other, and then compose the functions of this form? And suddenly, you've invented deep learning, right? You've invented deep models built on very simple functions like ReLU. So, exciting times. The problem is, how are we going to take functions like this and make them agree with data like we've been given? Right? I don't know if you've tried using deep learning models for regression rather than classification, or for extrapolation rather than classification, but you can get into trouble. It can be easy, it can be hard. And just as an aside, if you were worried that I was treating my functions as y equals f of x, all of these could instead be viewed as curves or submanifolds of some space, and really what we're saying is that each data point was generated by a projection from a low-dimensional space, here dimension 1, up to a high-dimensional space, here dimension 2. And what I want to do is somehow learn the parameters of this projection up. Right? This is, again, standard stuff that we all do. So let's look at a class of such problems, and let's try some strategies that we might apply. So here's a geometric view of a manifold fitting problem, a curve fitting problem. My job is to explain what's happening with this black data here. The lines aren't there, I've just drawn them in for visualization. So the black data is a list of samples, a list of big N samples Sn in some space. The red control points, these are 12 numbers, 12 parameters that control the shape of a piecewise defined curve. Here it's a spline because I'm kind of obsessed with the smooth curves, but a ReLU would, a set of ReLUs would work. And my job is to minimize overall sets of 12 parameters describing the 6 control points. An objective, which is somehow, please minimize the distance from each sample to the curve that we're searching for, and give me the curve that best minimizes that distance. That's a kind of a messy objective, right? So what do you do when you're doing an optimization problem? You first thing you might do is write some code to implement f of x. You might call it loss of x, and you might write some code. And you might shove it into some black box optimizer. And as you know, that's going to be more or less effective depending on how hard the problem is. You might notice that your code for f of x had a big for loop around an inner bit, and that for loop was essentially applying a similar function. So each of these f ends are different functions, but maybe it's the difference from the curve to each data point, right? So you might notice that I've got a sum of functions. And you might say, oh, I know how to deal with that. I'm not going to bother adding up all the functions all the time. I'll randomly sample subsets of them and do stochastic or batch gradient descent. If it were 10 years ago, you might have noticed if you're in a special situation where your functions are something squared, there's a fantastic algorithm called the Gauss-Newton algorithm, which is very good for sums of squared functions, and I'll tell you a little bit about it in a minute. And then you might say, okay, so sum of squares, I understand how to do that. But the function you showed me, you're going to say to me, is this horrible thing, right? It's a sum, and inside the function, there's a minimization. So am I going to differentiate through the minimization? How's that going to look? What am I going to try and do? Okay. Well, you might do that. I bet you've all thought of an algorithm. Let's see how well it works. Have you all thought of an algorithm? I think you have, right? In one, then the other, in one, then the other. Right, let's see how it works. Okay, so I'm going to apply a bunch of algorithms to some data. This is a problem that's kind of based on a true story. I got it from Neil Lawrence, so I should give credit. And I'm claiming that this problem is just the same as the problem of a bunch of computer vision problems like stereo camera calibration and surface fitting. It's a very similar problem to low-rank matrix completion with missing data to image denoising. It's got similarities to regression problems in deep learning, but I'm not going to close the gap, so don't be disappointed when I don't. What is this problem? So you've got to take yourself back to somewhere south east of here in about 1801. Right? So you're in Vienna, and you've heard some news that, well, everyone in Europe, wherever you are, you've heard some news that some Italians have been observing this thing in the sky, a guest planet called Ceres. and they've recorded observations of azimuth and elevation every evening for a few months. Okay? Now, normally you wouldn't have time to do anything about the data because it would take so long for the news to get across Europe, but luckily, or unluckily, the planet's gone behind the sun. So everyone in Europe gets these same 42 measurements, or 42 pairs of measurements, and they have a gigantic Kaggle competition, right? And or very small, Kaggle competition. And a Kaggle competition is someone has to predict where this thing is going to come out once it comes out of the sun. Your loss function is very interesting here. You're only going to get one run on the test data, right? You've got to predict where to stick your telescope on a given night sometime in the future. And everybody who's within a radius of, I don't know, 1 milli arc second or something is going to win. And everybody else is going to lose. Right? And no one knows how good the other people are, no one knows how much telescope jiggling there's going to be, but you just got to get as close as you can. Right? That seems like the best strategy in this case, is get as close as you can to the right answer. Okay, simple problem. I've got my data, some sample points, SN. I've got an absolutely known model for the manifold on which these data lie, right? My known model is it's got cosses and sines in it because, I claimed that they weren't useful for anything. They're very good in the sky where there are circles. And my known model is that I'm going to take, it's a circle, so cos t sine t, deformed by an affine transformation to make it an ellipse somewhere in the sky. And my model is, please, you say to the computer, find me the x's, that's the 6 parameters of the affine transformation, which minimize the sum over my 42 data points of, for each data point, please find me the closest point on the manifold, right? So find me the point on the curve that could have generated that data point. So I've got a sum of orthogonal distances as my objective. So fantastic, I know the model, I have the data. Let me fast forward to the right answer. So if I minimize this objective, I will indeed get this answer. And it's going to turn out that this answer is really good and you get the prize from the Queen or whatever. But a lot of times you might think, oh man, that doesn't look nice, right? You can work out, right, this inner min, this min function here for an ellipse. It's closed form, even in the 18th, 19th century. Yes, of course it is. It's a solution of a quartic. Right? So you can write down this whole function analytically, in some sense. You can differentiate through it. But what we normally do is we say, oh man, that looks like a lot of hard work. And anyway, I'm going to need to use a nonlinear optimizer to solve it, right? And who in their right mind would use a nonlinear optimizer? What you might do, so guess who wins this problem? Is it obvious who wins this competition? The answer to any mathematics question in Europe in the 19th or 18th centuries is always Gauss. Right? So Gauss wins the competition. So what would Gauss do? Gauss is very smart. So one thing Gauss wouldn't do is he'd say to himself, I know what I'll do. I'll find a nearby convex objective. Right? I won't do that closest point. I'll do some first order approximation, and then I'll do some other stuff, and I'll do some other stuff. And then I'll have a convex objective, and I'll be able to write a paper called A Direct Solution, or Direct Linear Least Squares Fitting of Ellipses. Gauss is so smart that he probably looked forward 200 years and found that some other idiot had written a paper called Direct Least Squares Fitting of Ellipses. And if you'd done what the other idiot said, you'd have ended up here. Right? So you're not going to be winning if you're going to find a nearby convex problem that is somehow just based on your intuition, probably like the problem you have. Notice that if you wanted to interpolate the data, you'd have been fine with this moron's method, right? But if we don't want to interpolate, we want to do a massive extrapolation. Right? We want to extrapolate all the way around this high curvature point. So you say, okay, that's not going to work, says Gauss, and this Gauss-Newton algorithm, which is invented around this time, which he claimed is used. So you might say, I can think of some other stuff other than sticking it into a nonlinear optimizer, and we'll get to the other stuff. Let me give you, no, I won't actually. Right, so as I said, this is a problem which is an instance of this curve fitting problem, which is an instance of a recommender system or model fitting problem. They're all instances of the same thing. So the solution you might invent is, I'm going to have a general algorithm for min of sum of min problems. And what I'll do is, I'll assume I start with a decent estimate, which is probably true, right? Remember, it's the 19th century, so you're actually allowed to just draw an estimate and say that's my best guess. That's perfectly fine behavior. I'm going to start with my initial estimate of the ellipse, and then for each of the points, I'll find the closest point on the ellipse. That means I'm going to argmin for each of the individual points, the closest point on the ellipse. And then you might say, all right, now I'll fix those variables, and I'll solve for the block of variables that are the ellipse, and I'll alternate the two. You might think to yourself, I've got a little theorem about that, right? You might prove to yourself that both of these steps must minimize the objective because they're minimizing blocks of variables, right? And you might think, you know what, I'll do that, and I'll run that algorithm while I think of something clever involving some other complex approximation. You might nowadays say, I'll stick it into gradient descent, and I'm going to claim that that has roughly the same behavior as the block coordinate descent, but I haven't really tested, but I kind of have. Or you might do the following. You might say, okay, I've got 100 data points, 12 unknowns, or whatever it is. You might say, this min of sum of min, because all the mins are independent, you can swap the min and the sum at the top. That's exact equality, not Jensen. It's just, you can swap them because the min of the sum is the sum of the min when the variables are all independent. And then you might say, instead of solving the 12-dimensional problem that I had at the top, I'll solve this 112-dimensional problem, right? Now, if you're any sensible person, you probably won't choose to solve a 112-dimensional problem, but if you're someone like Gauss, you'll probably think, well, obviously it's going to be easier, right, if I solve a 112-dimensional problem. How does the Gauss-Newton algorithm work? It creates a matrix of size 112 by 200. Sometimes it squares that matrix and makes a new matrix of size 112 by 112. And then it solves a linear system. It inverts that matrix, essentially. And you might do a quick calculation in your head and ask yourself, is 112 cubed a lot bigger than 12 cubed? And, I'm sure if you work it out, you'll think to yourself it's a lot bigger. No, it's not a lot bigger. I mean, yes, 112 cubed is bigger than 12 cubed, no news there. It's not a lot bigger because the matrix that you've got to invert has a sparsity pattern. That means the cost of inverting it, or the cost of back solving it, is linear in the big number and quadratic in the cubic in the small number, right? Exactly as you would have been with the inner problems in the block coordinate descent. Let's see which of them works best in practice. All right, so let me first of all show you video of. So this is wall clock video. It always matters if you're comparing second order algorithms and first order algorithms. You have to talk about the wall clock time, right? Nothing else matters because the iterations are different costs and so on. Even though I just argued them the same, it's hard to code them the same. I spoke too fast, right? So this is a wall clock video of the Gauss-Newton algorithm working on this data, giving this answer, which is a decent answer. I actually slowed it down 10x so you could see something, because if you get used to these algorithms, you'll get used to this picture. They just get faster and faster as they approach the optimum. This, on the other hand, is your block coordinate descent algorithm. Why is it going so slowly? It's going so slowly because every time you fix your t parameters, you fix your position on the manifold, you're almost forced not to be able to move the ellipse very far. So you're going to get this slower and slower and slower behavior as you approach the optimum. Sorry, I'm way over time. I'll stop at the end of this, and then we won't tell you anything about building computer vision systems that work. But let me tell you one more thing about this very simple problem. Something you might say if you're solving an optimization problem using block coordinate descent or any other method, you might want to know when to stop. Okay, so I have two curves here. Blue is Gauss-Newton doing its quadratic convergence. Black is some first order algorithm, the one I told you, block coordinate descent, doing its essentially linear convergence. This is the point at which successive function values are smaller than 1e minus 12 apart. Right, so you might think I'll stop because they're like 10 to the minus 12 apart. They're very close. I'm going to say no, you can't stop there. Somewhere down here is the point where successive function values are 0 apart. 0 float. Okay, or double, doesn't matter, right? So iterate function is exactly the same value. So now you're going to say to your supervisor or your student, whichever one you are, look, it's converged, come on, right? It's the same value. It's been the same value all week.
And then suddenly, just as you look at it, the last floating point bit ticks over, right? And you drop another bit. Right? And you were saying, Andrew, come on, you're obsessing about this is nonsense, right? It doesn't matter, look, that the value hasn't changed at all out here. Well, let's have a look at the test data. Okay, so here are the test curves. The test curves are for the problem that we're actually interested in, predicting when the thing comes out behind the sun. How badly would you do at each of these values? And look at what happens. In both curves, you get exactly the same behavior. You're going to overshoot. Like the model may well go through the correct answer on its way to the answer that it's fair to report. Right? But this is the test error that is fair to report. You can't report this in here because you don't have any other data. You have to minimize the function you were given. This is what happens when you're doing the slowly converging thing. So even while it's converging, making zero change to the objective, it's making significant changes to the prediction because the prediction is really far from the data. Now, you can't always do this. We know that deep learning models generalize well anyway, so it's not a problem that, when you're doing an interpolation. But if you do have an extrapolation problem, and I'll show you one in a second and then I'll stop, it can matter to squeeze the last few percent or a few tenths of a percent out of your objective. And then the final observation about this is, if you happened to use the termination criterion that I favor when using first order methods, which is the code is while not control C do theta plus equals minus lambda grad B, grad F. I haven't noticed there's an early stopping point here where you could accidentally do better. 50% of the time you might do better because the model might overshoot through the data. Might do, might not. What I haven't realized is this is, of course, is 99% of the runtime because it's all on log scale, right? The time is on log scale. So if you hit Control C, you're almost always, in this particular example, going to be lucky and report an artificially low test error. Yeah, I'm not saying there's no way to cheat using that. It's just you might accidentally be lucky in that situation. All right. Let me draw you attention to a paper benchmark we ran recently. It doesn't matter what it is. We benchmarked some automatic differentiation packages for smallish models. So we're looking at problems with 1 million down to 100 parameters. The big picture from this graph is that, if you use AutoGrad and Python on a small problem, it's not going to work, right? You knew that. If you write hand-coded C, it's probably going to go fast if you know what you're doing. You knew that. What I did not know before we did this is how many of these ticks there were going to be on the y-axis. Right? I did not know that you were going to get 4 orders of magnitude slower if you just put the thing together in AutoGrad. Now, not trying to alarm you, right? This is for small problems, vision-like problems, where I'm multiplying 3x4 matrices by 4x1 vectors, right? I don't have a 4K by 4K weight matrix that is clearly going to go fast with large problems. Yeah, okay, so I will show one example of one of these block coordinate descent versus ICP, and then I'll stop. So what I'm simply showing here is that if you have the problem where you have data from a camera that gives you 3D data, and you want to fit a model of the human hand to that data, I'm saying do use, during the real runtime process, do use a nonlinear optimizer. Sounds crazy, right? Why would I do even 2, 3, 4 iterations of nonlinear optimizer when I could just use a deep learning system and get a pretty good estimate? I think my message is going to be, and I think I do this more and more now, don't try to do the full job with one technology. So what I mean is, of course it would be moronic to try to start from an arbitrary initialization in any situation and try and fit using nonlinear optimization a model to data, right? You'd have to do random restarts, you'd have to do a bunch of stuff. I'm saying it's also not a good idea to try and do the whole thing just with deep learning, not because it can't be as accurate, it can be as accurate, but you're going to waste so much model capacity getting your last few millimeters of accuracy when you can easily do it with a fitting to a known model. And then the final thing about fitting to a known model is, of course, it's super explicacious, right? You can exactly tell when the system isn't fitting the data. You can exactly tell if I report to you the model that's clearly upside down or clearly not fitting the data. it's easy for me to work on. Okay, I'll stop there. Thank you very much.
So I was an intern at Heuritech a few years ago, and I was helping organizing this meetup. So it's great to be invited here now. So I'm PhD student in INRIA, Université Paris-Saclay, and Facebook AI Research. And I'm not going to show you some fancy new application of deep learning, but I'm going to introduce you a theoretical point of view in machine learning in general, and what it has to say on deep learning in particular. So the question I'm going to ask is, do deep learning have too many parameters? So why is this question even relevant? From a machine learning perspective, a good model is only a model which is able to predict well on test data. And it seems from experiments that when the models are getting bigger and bigger, the results are getting better and better. But from a classical statistics point of view, we know that we don't like to have models which have more parameters than we have data samples. When there are more parameters than data samples, it means that we don't have theoretical guarantees and that we can overfit. And we know that deep learning models are able to overfit. We know that if we train deep learning models on random labels, for example, it has been done on ImageNet, a famous paper, they are able to memorize the entire datasets, even if it's random. So it seems that there could be a problem, but in practice there is not. So I'm going to introduce another point of view on that problem, which is the point of view of general induction theory and information theory. So what is induction? Imagine you are in front of this sequence, and I ask you to predict the next digit, 0, 1, 0, 1, 0, 1. What would you answer?
0.
Yeah. So I'm a mathematician. So I would like to say there is no answer. There is no possible way to deduce the next digit from this sequence. There is no logical way to answer to this question. But we have a kind of prior on the world, which makes us answer to this question. So this would be a mathematician answer. What would a dummy machine learning algorithm say? Probably it would assume that the data are IID and it will answer 1/2, but that is not very useful. And what everybody would say is 0. So why are we saying 0 here? What we're doing is that we are trying to find the simplest explanation, the simplest model which could have produced this data, and then using this model to predict the next digit. So this is a very general principle of inductive reasoning, which is called Occams razor. And it's quite old. And it could be stated that way. We select the simplest explanation which explains the data. This is used all the time in our everyday life. I mean, if you are looking at people playing at a game and you can learn from what they're doing, the rules of the game, it's also a foundation for all empirical science. For example, it's not possible to test that the laws of physics are the same everywhere in the universe. But this is what we have observed, and it seemed the simplest model we can have on this question. Okay, so we have this general principle for induction. We should always take the simplest explanation for the data. But when it comes to deep learning, it seems to be a paradox. The models which works the best seems to be the most complicated one, the ones with the most parameters. So there is a kind of paradox here. And we could state it that way. Do deep learning models have too many parameters, or is Occams razor wrong? And this is what we're trying to answer here. So for that, we'll need to formalize Occams razor, because this definition is not very usable in practice. And there's a tool to do that, which is information theory. So what is an explanation? An explanation or model for here a string, but generally on data, is a program is a program whose output is x. And the complexity of an explanation is its length. So this might be complicated, but it just means that what is an explanation for this string? It means it's just a program, like a Python program on your computer, which outputs this. And what we are looking at the complexity of the explanation, so it's just the length of your program. With this notion, we can define the Kolmogorov complexity, which has been introduced by this guy, who is not Kevin Spacey. The Kolmogorov complexity of a string is the length in bits of the shortest explanation whose output is x. So this is kind of the intrinsic complexity of the data. And how we can formalize Occam's razor is that we're going to look for the model or the explanation of the program with the lowest complexity. So it is the program or the model which compresses the most the data, the shortest program which explains the data. So what is the intuition? Why is compression the right way of formalizing things? Imagine that Newton of the 21st century, is looking at a video of an apple falling from a tree, and he wants to compress it. The first thing he can do is just encoding each frame of the video one after another, like PNG file. This is quite expensive. Another thing he can do is understanding that the apple is following the law of gravity. And then he can just encode the first frame of the video, encode the law of physics, this is one Python line, and then deduce from the first frame all the following frames. And then he had compressed the video. So the idea here is that any structure in the data we can find can be useful to encode the data and compress the data. So the entire idea here can be summarized in just one sentence, which is comprehension is compression. And when you think about it, in fact, when you are doing compression and when you are doing prediction in machine learning, you are doing the same thing. You are trying to find some structure in the data. When you are doing prediction, you're trying to find some structure to predict on new data you have not seen yet. And when you are doing compression, you are trying to compressing with the structure. So we have a new point of view on learning. What is learning? What is doing inference? What is the difference with the classical formulation of machine learning? So in machine learning, how do we know that we are generalizing? We have usually a trained dataset and a test dataset. We learn on the trained datasets, and then we check on the test data that our model is okay. So this works really well, but it's not a really satisfying definition, and mainly because the hypothesis behind this formulation is that the data are coming from a true probability distribution and are IID. This is why we can have a train set and a test set. But on the example I gave you of the sequence 010101, you can't have really a train set and a test set. It doesn't really have a meaning. If you take the example of the laws of physics and you want to check, you want to be sure that they are the same everywhere, what would be the true probability distribution of going everywhere in the universe? And you can't even test it. And even on real datasets people are using, like ImageNet, there is no true probability distribution. You don't have an infinite number of images, and they are not IID. They have been really chosen by people to have a large data set, so it's not IID. So it's a useful hypothesis, but it can be a problem to found what we call generalization on a hypothesis which is quite wrong. So here with this theory of general induction and information theory and compression, we never need to assume that the data are coming from a true probability distribution. We just try to compress it, and if we have a model which compresses it, we don't care if it's wrong, we don't care if it's the wrong model, it just works. So now we search programs which compress the data. Okay, so now we might think that I'm going quite far from real problems in deep learning. So let's see how we can formalize the supervised learning problem with this setting. So let's take the case of MNIST dataset, which is the hello world of deep learning. And so it's a dataset of 60,000 images of digits, and we want to recognize the digits. How can we formalize that in information theory? What we say is that we have two characters, Alice and Bob. Alice had the entire dataset, so all the images and the labels. But Bob only has the images, and Alice wants to send him the labels. How can she do? The first thing she can, we assume that the images are ordered. The first thing she can do is just send him the file with all the labels. She, without taking into account the fact that he already had the images. So how much does it cost? For NIST, it's 60,000 samples. There are 10 categories, so it costs around 200,000 bits. This is not so much. But she can do better, and she can do better by using a model and using the fact that Bob already has some information and with the images. So how can she do? She can first send a model, here B, and then use this model to encode the data. So how, for example, she can send a model which has on NIST, let's say, 99% of accuracy. That's not so hard, and then the model is not right all the time. There are some errors, but Bob wants the exact labels. So she only have to send him the errors of the model. So here you see that there are two terms on the cost of the compression: the cost of encoding the model itself and the cost of encoding the errors. So Alice needs to find the right trade-off between the cost of encoding the model, which is the complexity of the model, and the cost of encoding the errors, which is how well the model fits the data. So this is a way to encode the errors. In fact, the right way to encode it is to use the fact that the model is a probability distribution and use Shannon code of this probability distribution. So I will try to explain briefly how we can use a probability distribution to encode some data. So let's take a completely different example and to explain the basics of classical information theory. Let's say you have a huge log file like this one, in which there are a list of words. It's only a finite set of words, and most of them are a success, and there are also some warnings and some errors, and you want to encode it. You know that the set of words is finite, so you want to give a sequence for each word, a short sequence, and in binary encoding. So the first way to do it is there are around 16 different words, so give 4 bits encoding for each word. But this is not an interesting way to do it, because as we see, most of the words are success. So as you see in the encoding on the top right of the screen, you spend a lot of bits to encode success, while it happens a lot. So you would like a shorter code for success and longer one for the errors, for example. So this can be done with Shannon code. And for example, here, this is a real code. So here you see that there are less green digit. This means that you are spending less bits to encode what is here more often. And you are doing this by using a probability model. So you say that you give a probability 1/2 to success. And so you only code success in 1 bit, while for this error, which doesn't happen often, you code it in 6 bits, for example. So this is just to show you how we can encode data when you have a probability model with code. This is how we design code. But let's get back to how we can encode the NIST datasets. So we have this equation here, which says that you can encode. There are two parts in this compression cost here. The first is the cost of encoding the model. The second one is the error, the cost of encoding the errors of the model. I want to spend just to have a few remarks on this equation. If there's only one equation to remember from this talk, it's this one. So the first remark is just take a few examples. The first one is what happens if you take a model which totally overfits on the dataset. So it means it's memorize the entire dataset. Then the second term of this equation is 0. There's no error. The first term is huge. You have to memorize everything. So you don't have any compression because all the data is in the first term. On the contrary, if you take the uniform distribution here, the cost of encoding the distribution is 0. It's free to encode the uniform distribution. But the error term is huge, and you do not have compression. So you need to find the right trade-off between having a model which fits the data to have a low second term, and a not too complex model to have a low first term. And just another remark, you can see that this second term, in fact you already know it if you are doing machine learning, it is the loss you are usually using. It is the loss of classification. So what does it mean? It means that in fact when you are training a model, you are training it to encode, to compress the data, to compress the data well. And it is exactly the same loss, and the only difference here is that this information theory and learning says that you need to take into account the cost of encoding the model and add a penalty, regularization on the model. And this Kolmogorov complexity of the model is like a universal regularization on all the possible models. So, great, but what can we do with deep learning now? I started to work on this because I learned at the beginning of my PhD this theory of information theory for learning, and okay, I like math, so I was happy to learn everything. And then I had a discussion with my advisor, and I told him, okay, it seems good, but I think it's wrong, because it doesn't work for deep learning. Let's take the example of NIST. So you know that NIST costs 200,000 bits to encode with the uniform code, so without any learning. And if you take any deep learning model, which has, for example, 1 million parameters, it's not a lot for a deep learning model, it will cost a lot to encode the model itself. So, for example, if you encode the model with 32 bits per weight, it will cost 32 million bits only to encode the model, without even taking into account the errors. So you are not compressing the data at all. And I said that we say in this information theory viewpoint that a good model is a model which compresses the data. So it seems really extremely bad. What we can do, which is a bit smaller, is that we don't really need 32 bits per weight. We can have a low precision. We don't need so much precision. But even with 1 bit per weight, it's still too much. It's still 1 million bit for the entire model. So that's too much. We also tried some Bayesian method. I'm not going to talk about it. Variational methods linked to variational autoencoder for those who know that. But I'm not going to introduce that. But so there seems to be a paradox here. The model which generalizes well is the model it cannot compress the data. So this is why. This was the first question: is Occams razor wrong? So we found a way to encode all the data with the model, while never encoding the model itself. And the way to do it is quite simple, in fact. So let's say that, so we have Alice and Bob, and Alice first sent the 100 first labels with the uniform code, so that costs a bit. But then Bob and Alice both train a model on these data, and then they use this model, which is not so good because it only had 100 labels to be trained, and they use this model to send 100 new data, and they retrain a new model, and so on and so on and so on, and they send only packs of data. So the first packs of data are quite expensive to send because the models are not good. But when you are sending a lot of data, the model is getting better and better, and at the end, it's really cheap to send some data because the model is very good, and we can compute practical compression bound with that. So, for example, on NIST, so I said NIST is 200,000 bits. So you can compress it on a little bit more than 4,000 bits, so almost 50 times 50 compression rate. And we did that for Sci-FAR2, and we have a 5-time compression rate. And here on the right, you can see how much it costs to send each label. So you see at the beginning that it's quite expensive to send a label, but for example, for the purple curve, after 1,000 labels, it becomes cheaper than the uniform, and after 10,000, it's really cheap to send a label. And here you have the compression ratio of the method. So just to conclude, we found that there's no paradox, in fact, and we bring back together with this method the induction point of view, the information theory point of view, and the machine learning point of view on what is a good model. And we see here that despite their huge number of parameters, deep learning models can compress the data even when we take into account the fact that we have to send the model itself. And so we see that even from the information theory, which tends to select the simplest model, even from this point of view, deep learning model seems not too complex and with not too many parameters. Thank you.
So hello everyone. I try to make my English as understandable as possible. So I'm Stefani. So I'm here with Photobox, and I will talk to you a bit about what I did during my internship there. At Photobox, when I was still a student at Pierre University here in Paris, with Christina Prian, with you tonight, on landmark recognition. So recognizing famous landmarks or touristic sites in pictures. I'll start by a quick context. And who are we, Photobox? What do we do? Photobox is a European leader of personalized photo products like photobooks, calendar, mugs, even aprons. And it's more than 1 billion photos are uploaded every year on the website. And for our artificial intelligence team to treat and analyze this photo, we need this process to be as fast and as real time as possible. So just for quick context, why do we want to be able to recognize landmark? So for our clients, landmark are important picture. They often take this kind of objects in their picture. And it's also key points in the travel, the trips, or the memories. And on our side, why do we need deep learning for it? Mostly because our GPS metadata is not enough, so we don't have access to this information as much as we want to. And so we have to extract this directly from the photo content. And I'll show you in just a few slides what are some of the challenges. So first of all, the GPS is the perfect way to guess the landmark in the picture. So here's an example. On the left, it's a picture of the London City Hall from the Tower Bridge. On the right, your GPS location will be at the City Hall, but the photo content is the Tower Bridge. Now the challenge are similar landmarks. So we have for cathedral. Even for a human eye, it's sometimes difficult to see the difference. It's also one of the reasons why we want to have an algorithm that do it for us. I could also have taken found landmarks that are even more similar, like the exact replica in Las Vegas of Paris and Venice. And the last challenge, which applies a bit more to our problems, is the photo diversity we're dealing with. So we're dealing with everyday photos, and for one landmark, we will have pictures from almost every single point of view, angle, range possible. And most of the photo we have are often selfies or picture where the landmarks, so the thing we want to detect, is in the background and is not the focus point of the picture. So that was for the context and the problem. Now I just spend a few slides talking about how is it tackled. So this landmark recognition problem, it's like place recognition, and it's often done through large-scale image retrieval, so finding similarities between billions sometimes of images. So I split the process in three steps. So feature extraction, bit of works around the feature, and the retrieval system. The main point here is that for a long time, feature extraction was done through image processing tools, like I've listed some of them here. And really very recently, it has been VGG, ResNets, and deeper model have been used and have performed as well and now better than most of these techniques. So it's 2016, 2018. Important part between the extraction and the retrieval system is that since we will have to find similarities between billions of images, we want to have compact and small enough features so that our retrieval system is not huge. And so a few techniques to do that, like pooling or compression methods. Now the heart of the system is retrieval. So it's often a very basic nearest neighbor search over all the data, and then you will have different tools and methods to get stronger assurance in your prediction and in the images you retrieve. So I've mentioned a few of them because they're quite interesting. For example, database augmentation. So you will first find the top 10 nearest neighbor, and then you will make a mean or something like that of your image and its neighbors, and do another search of 10 new neighbors. So it's a way to go a bit further. Query expansion is the same spirit. You will find your 10 neighbors, and then you will select all of the 10 neighbors or some of them, and do another search with those neighbors. So to go a bit further in the neighbor graph. And the last method I will mention is a geometric or spatial verification, where you will try to directly match the features of two images. So this is quite a heavy step. I will mention it a bit later in an example. But before that, so as I said, deep learning methods have tackled this problem really nicely recently. And so with that, we've seen a new datasets dedicated to landmarks that have been published. For example, this year, Google published a giant dataset of 30,000 landmarks with a Kaggle challenge. And so there's a big square here is supposed to be a trophy emoji. So this is the team that won the challenge. So I just here put the different methods they used for the steps. So like many Kaggle competition for the feature extraction, they used not only ResNext, but it was like an ensemble method of ResNet and DenseNet. But this is the most simple pipeline. For feature aggregation, they use PCI whitening for compression. The remap thing is on the papers they are yet to publish. And then the retrieval system with some of the methods I mentioned before. And the key part here is that this, so the simplest processing pipeline they have, it takes a minute to process 100 images on 4 GPU. So we have to deal, in our industrial use case, we must deal with photos on real time, and most of the retrieval, if not all of the retrieval architectures, take too long and are too heavy on inference for us to work with. So what we did is shift a bit the problem and try to adapt some of the feature extraction methods into a classification problem at the end and not a retrieval system. So it's mostly because we need the inference to be faster, and because feature extraction and feature aggregation tools and algorithms that have been published are still good enough to describe our image, we only need to change the last part of our system. So I mentioned a quick word on the dataset we used. So first of all, another reason why we didn't have problem thinking about this problem in a classification point of view. Our problem was to detect and predict the landmark in one picture. We don't necessarily want to find similar images that the customer upload. And also, we didn't have any problem finding beforehand the classes we wanted, because we have internal statistics on what are the landmarks or what are the countries that are visited by our customer. So we found 263 landmarks, so classes now, and at the end it's around 53,000 images, mostly from the Google datasets published earlier this year. So now I'll try to go through step by step on what our model use. So first of all, for the feature extraction, we use a method called DELF. So it's Attentive Deep Local Features, and it was published last year by Go and at Google, and it's because they achieved very good performance. It's one of the reasons that motivated the publication of the Kaggle challenge. And so it's a ResNet for feature extraction. The important part is a yellow brick. So it's an attention layer that will focus on the most important features for our task. So here, landmark. Just before that, so we take as an input an image, and we transform this image into 7 different scales of this image. Each of the scale will go through the ResNet 50, and that was also fine-tuned on landmarks images and produce their own features. And now what the attention layer is in this case, so it's a scoring function. So it's a 2-layer convolutional neural network. And each of the features, so the red dots here, will get a score at the end of this attention layer. And only the features that passes a certain threshold on the score will be selected. So as you can see, and this is also why we really wanted to use this methods for feature extraction, is that we are basically keeping only the features that are related to our landmarks. So in practice, we are removing features related to sky, trees, sea, and faces. So as I said, with photo we're dealing with sometimes selfies or where the landmark is in the background. It's very important for us to work, to be able to work with this kind of method. Now it comes at a certain price. Because with the attention layer, we are only selecting a few features for each image. So every time an image is in the model, we will have a different number of features that are selected at the end. So it's quite difficult after that to imagine a standard classification algorithm that takes a variable size as input. So we need to to get a fixed dimension as the input. So what we use for that is an algorithm that is pretty well known for landmark recognition and image retrieval. So it's VLAD, a vector of locally aggregated descriptor. So beforehand, we learn clustering of our data. And every time an image goes in inference, we'll assign each feature, each red dot, to a cluster. For example, this red dot will be assigned to the cluster 1. And then the image representation is done through the different clusters. So if we consider, for example, a k-means of 32, each image will be represented by 32 components, so the 32 clusters. And for example, the blue cluster here is component 1. Its final value will be the sum of all the distances of all the features that were assigned to him. I hope I'm clear enough. It's basically a bit more, a bit smarter and subtle than just all assignments to a cluster. And it's quite effective. So here, for each color, it's a cluster. And as you can see, so it's 4 different landmarks, but you'll find the same cluster around the same structures for these pictures. And in practice, the VLAD representation enabled us to be able to describe the image with very few features. So 32 or even 24 was good enough to have good results. And our classifier, in the end, a fully connected classifier, became more efficient with few parameters. And so from quite a big amount of features at the beginning, we were able to compress and get a compact information and train efficiently a simple fully connected to make a prediction. I'll just mention a few additional steps we're doing since it's also critical for us not to predict false positives, so not to guess wrong. And here's an example. So we're doing a little bit of spatial verification, but much less than the usual spatial verification step in retrieval. So we're just comparing our input image, the image in inference, with images in our database of the prediction, and simply checking if they have enough features in common, or rather features that are close enough. So here's an example where the model gets wrong, but through this step we were able to remove this prediction. Another step is using the metadata. So I mentioned GPS. Unfortunately, we don't have it that much, but when we do, we check if it's consistent with what we predicted, of course. And another important bit of data we have is not only we have the photo, we also have the context of the photo, so the photos that were taken in the same period of time. And what we do, for example, take pictures taken in the same day or the same afternoon, and check if the prediction of the model is consistent. And if we find that a landmark that is supposed to be in London was predicted in Paris, we will just remove it. So I will talk a bit about the results. So remember, our main goal was to have a faster processing time without losing too much accuracy with our model. So this is on a single GPU, and the whole pipeline takes for 100 images less than 30 seconds. And now the most expensive part of the model is the feature extraction through a Google model. And it's no longer the retrieval or last step. So now, bit results on the accuracy side. So the first bar is our validation accuracy with our model. So on our 263 classes. So it's quite good, and it goes pretty fast, as I mentioned, less than 30 seconds. On the second bar is, so we tried with the same architecture, with the retrieval system in the end and not the classifier, and with a on-stack, so a stronger spatial verification. So you can see it takes much more time. And the other interesting bit was that for a small amount of clusters in VLAD, so 32, here is all 32, retrieval performed worse. But for bigger, like 256 or 512, the chart here will get inversed. Like retrieval will be better than the fully connected, but not good enough. And finally, the last two methods we're using, we're trying to have the lighter and simplest pipeline possible. And so we are trying some more classic image model. So just fine-tuning ResNet on our data. So we without attention and without VLAD, just to have the fastest pipeline possible. Now our goal is with more and more data to be able to get closer to the first method mentioned. So I mentioned a bit and talked about VLAD and the cluster size. So this is a test data set, different than the validation one, with 1,000 photos from Google. And as you can see, so the key bar is the blue one, is how are we able to detect, how many landmarks are we able to detect, because we are often quite accurate in our prediction. And as you can see, really perform better with few clusters, so few words to describe each image. Now I'll show you some quick examples and start by when it doesn't really work. So obviously when a landmark is obstructed or it works like this one, it gets more difficult. Another, like the Big Ben, sorry. Another difficult problem is the city skyline here. So on this picture, we have 4 landmarks in our data set. And so which one should we predict? It's not that easy to say. And also, how do we know that in our training, validation, and test data set that those kind of images are correctly labeled? Or how do we label them? It's kind of an open question. And then the 2 examples at the bottom are the main difficulty of the problem and where our model is a bit less performant is when it comes to pictures that are not landmarks. So for example, this beach in Brittany and this random skyline. We don't want to predict a beach in Thailand and Manhattan, but it's difficult not to, especially because of the attention. And for those 2 pictures with mostly skies and sea, very few features will be selected after the attention. Now, example that works. So all those pictures are either myself or Creative Commons. When the landmark is at the very background of an image, for like the Golden Gate on the upper left, or when and this is the kind of photo that everybody take. You have selfie and half of the photo is your face and the other half is where we want to detect. Or for the Machu Picchu, here I wanted to highlight the generalization power of this deep learning model. Just on very different places of the Machu Picchu, it's still able to detect. Now, other examples where the landmark is in the background, like Saint-Étienne-du-Mont near the Panthéon, or for the Sacré-Cœur, where there's just a small part of the actual landmark in the picture. And lastly, on the right, so it does not work all the time, but it's pretty surprising how often does it work for the replicas in Las Vegas. So the model is able at the end to learn other key aspects of the area and guess correctly if it's in Las Vegas or Venice. So I will just take a step back to summarize the bit. So first of all, what we are still trying to do is have an iterative process to improve our data sets with some of the pictures we are labeling, and improve our models by training them on the new data sets. A simple stat to show you why it's also important for us. So we did an experiment on travel albums where we have very few information on where those pictures were actually taken and where our customers wanted to go in holidays. And so now by using this model, for example, we will be able to see the places where they went in around 75% of the albums. It's quite a big step. So lastly, I'll end there just to say that we did not invent anything, but the key part is we're trying to adapt performing models to our very difficult cases, and especially timing-wise, because we want to have the fastest possible inference time and those models are often quite a bit heavy, tends to get heavier and heavier. So that's it for me.